Hello, everyone. Thank you for joining today's webinar, Essentials of Grip and Fixture Selection in Force and Torque Testing. Before we start the webinar, I just wanted to go over a few things. So this is the McMesson webinar. McMesson is part of the Physical Properties Testers Group, or PPT Group. The PPT Group is a family of brands, all of whom are experts in the design and production of physical properties testing solutions. These solutions cover a range of physical properties, including tensile and compressive testing, torque testing, textile analysis, and real-world dynamics such as shock and vibration. The other companies within the PPT family are Lansmont, James Hill, and Alluris. If you're interested in learning more about these divisions, you can visit our events page and see the content and on-demand webinars we have available. I'll put a link in the chat box shortly for you for easy access to that. But back to McMesson, we have a technology lab located in Sterling, Virginia, and Slinfold in the United Kingdom. We established these labs as a way to support our customers through education, proof of concept, and testing demos. So please feel free to reach out to us if you have any particular physical properties testing needs or grips and fixtures, as we're talking about it today. We have a fully global team that can support you. And then let me introduce some people on today's call. Moses DeRocha is our presenter for today, and my name is Sharon Smorenberg, and I'm one of the organizers. We have various support staff throughout the United States, Europe, and Asia. So if you need information or support, we have someone that can assist you in your region. And last but not least, we do want to keep this interactive, so please feel free to ask questions. You can use the question box throughout the webinar to type in any questions you may have, and we will then address these questions at the end of the webinar if we have time. If we don't have time for them, we will come back to you with an answer directly to your inbox. This webinar is going to be recorded. You will get a copy of the recording to the email that you registered with. So if you want to review anything for additional clarity, or if you have a colleague who was interested in attending but wasn't able to make it, please feel free to pass this along to them. And with that, I will turn it over to Moses.
Thanks, Sharon, and thanks everyone for making the time to join our webinar this morning on the essentials of grip and fixture selection in force and torque testing. Now, usually, this is a two-part where we discuss compression by itself, tensile by itself, and then when there's time, we'll throw in torque. But again, so we've kind of combined, condensed the whole thing into one presentation today. So we're going to be moving at a slightly faster pace, but it's supposed to be an essentials of, so it's more of an introduction rather than an in-depth, as in an application-centric presentation. So just a quick glance of the agenda here is we'll look at the critical elements of repeatability and consistency. Even though that's showing at the beginning of this agenda, we're actually going to look at it at the end, because then that makes more sense, having looked at the importance of grips and fixtures in testing, in compression testing, tensile, and torque. So that's essentially the areas we're going to be covering today. So we'll start with compression testing. If we just started discussing grips and fixtures in isolation, it would be kind of abstract and not really relate to much. So I wanted to give a quick primer on what compression fixtures are all about. To do that, we'll have to look at what compression testing is all about. So essentially, compression testing provides data on the integrity and safety of materials, components, and products, whether it's raw material or finished products. It involves applying uniaxial force or compressive force to measure the performance of a test specimen under a compressive force or load up to the point of yielding or failing or breaking. The sample under test, as we mentioned previously, may either be a specimen of raw material or an actual finished product. Test samples are usually compressed with a compression plate or a probe, and force or load is applied at a constant rate of speed. Now, this happens whether you're testing to a specific ASTM or ISO standard, or if you have your own in-house standard that you're testing to. And then subsequently, the data that is collected can be plotted on a graph that shows a force versus extension or a force versus displacement curve. Or in cases of materials testing, you'll see a stress versus strain curve. Compression testing is performed with either plates, probes, fixtures, and that's essentially what we'll be looking at in the next few slides. So the objective of compression testing is varied, but primarily it can be either a destructive or a non-destructive test. And it's intended to measure the force resistance at a specific deflection or displacement, or it will measure a deflection when a specific force is applied. And in other instances, you measure the force all the way to the point where the sample either fails or breaks. Sometimes in materials testing, you'll also like to measure the yield, which is the point of deformation, in addition to both the force at the displacement or the deflection at a known force. So these are essentially the main objectives of compressive testing. And you'll likely also find this in most product testing. So what do we use in these types of tests and why? So we'll take a brief look at compression testing grips, plates, and probes. We'll start with the most popular. Anytime you hear compressive or crush test, your mind immediately goes to some type of a plate or platen or a probe, but mostly compression plates. And these will come in different sizes and materials. So they can be depending on the size of the sample that's being crushed. Now take this from, if you think of a pellet, right? A simple, small 3mm pellet, all the way up to a garden planting bucket, right? Something that's that wide, that has a wide opening, or something that's small. So depending on the size of the sample, you'll be able to range between what's appropriate as far as the sizing. You look into overlap the actual sample, either the sample diameter or the sample opening, and also whether the sample is closed or open. You might opt for a vented or a non-vented. Now, very quickly, if you're testing an open sample, let's say it's a container, think of a plastic container that's open, in order not to build up pressure, which will essentially spike the compressive forces, you're looking to use a vented compression plate, which lets the air out, so you can pretty much concentrate the compressive force on the structure itself. If you have a bottle that is already pre-filled with product and capped, then you could essentially use a non-vented compression plate, because essentially what you're trying to do is duplicate what happens in the processes of filling, packing, storage, transportation, so you know whether to stack them 10 high, 15 high, and make sure that the bottles on the bottom will still survive and not just collapse under the load. So that's what top load testing would all be about. In this case, that form of compressive testing. There are also rubber-faced compressive plates, and that's plates that are designed to prevent any slippage. If you have samples that have a really smooth surface and you don't want the samples to slip or slide, what you do is you provide the rubber-faced grip that provides the necessary traction that prevents the plates from slipping. There are also self-leveling compression plates that adjust to uneven surfaces to maintain that compressive force, so there's no sliding or slipping during that test. And these compression plates will come in different shapes. So if you can imagine, you're testing a plastic container, or you testing a small pellet or catalyst, as opposed to say a corrugated cardboard carton, you can either opt for a round compression plate or a square or rectangular, depending on the type of sample you're testing. But compression plates would usually be used in, as I mentioned, top load or sample crush testing, burst or break testing, and then some push-up testing. Compression probes, on the other hand, are, again, you'll find the same requirements here. They come in different sizes depending on the type of sample being tested, and these can come in aluminum, steel, or plastic, or Delrin. Sometimes they're even 3D printed if it's a real sample that is kind of really sensitive, that requires very minimal forces, and these can be either flat, round, radiused, or sharp. So again, you test into an ASTM standard or an ISO standard that requires needle puncture or a puncture or penetration test. Obviously, a flat-faced sample, it's going to push and not necessarily puncture. So you're looking for something that might have a sharp edge. So in all of these grips, the selection would depend, one, on the type of test application and what the objective of the test is. So you'll find probes used in touchpads and touchscreen testing, puncture, penetration testing, push-out testing, crush or burst testing. So the other day we were just testing gummy, as in gummy bears. So an application like that requires the highlighted item there, that is the round plastic ball or compression probe that kind of simulates a crush to test the firmness of gummy bears. So again, the application will pretty much dictate the type of fixture being used in the compressive test. And then there are the custom compression plates. So sometimes, you know, it might not be a lot of force, but the sample might be huge. And so you're looking for a wider area, and you're also looking to concentrate the force on the entire surface area of the sample. Case in point, the corrugated cardboard, which is the carton crush. This guided rod type of compression assembly is something that you would use in an application like this, where you slide the box in between the probes, and we make sure that the force is distributed evenly across the surface of the cardboard. And this can also be sized down to even smaller samples. So again, depending on the size of the sample, it could be either really large or really small, but both of those are not usually common off-the-shelf type applications, but those are also available, and these are the types of compression fixturing that you would use in applications like carton crush testing, glass break testing, or touch and actuation testing. All right, next part of this is tensile testing. Once again, we'll take a quick look at a primer in what tensile testing is all about in order to focus in on the types of fixtures that are used in tensile testing. Again, tensile testing, when the integrity and safety of materials and components or products are at stake. Tensile testing is performed, which usually involves just applying, again, uniaxial force to measure the performance of a test specimen under tensile load up to the point of yielding or breaking. Once again, it could be a sample in raw material, or it could be a finished product. Test samples are usually gripped at the top and the bottom and pulled at a constant rate of speed until the sample yields or breaks. Data collected can be plotted on a graph showing a force versus extension. This is typically in a force test where we're only looking at the force at break, or on a stress versus strain curve where we're looking at things like the yield point of deformation, things like Young's modulus, the offset, and so on. And so testing is usually also performed using tensile grips and fixtures. And in the next few slides, we will look at what some of those grips and fixtures look like. Now, once again, just as we saw in compressive testing, the objectives of tensile testing are very similar. It can be either destructive or non-destructive testing. Sometimes the questions come up on why choose one over the other. I'll quickly explain. A non-destructive test is essentially a 100% test, where let's say you're a watch maker and you're looking to test the straps, the strength of the straps on the watch. So they need to withhold or meet a certain minimum threshold of, say, 20 pounds of tensile force. So every single watch comes off the line, grab the top one part of the watch, pull the strap, one part of the strap on the top, one on the bottom, pull it to 20 pounds. If it meets that minimum standard, it's a pass. Put it in a bin, get it ready for market. That's what we would usually call a non-destructive test, where you're doing a 100% test. Similarly, you can do this on several different types of fixtures. Take, say, for example, a zip tie. If the minimum tensile force for the head that requires the head to break would be 200 pounds. So we would say as long as it meets a 100-pound threshold, that's a pass, right? So you can test to whatever that minimum requirement or that minimum threshold is. If it passes, great. Obviously, if the sample fails before it meets that minimum threshold, that's a problem and something needs to be looked at. Is it too little plastic? Is it too little material? What went wrong and why aren't you meeting your minimum thresholds? And that's essentially the scenario in a non-destructive test. A destructive test is more common, where you're looking to test to the point of failure. You just want to see what it's going to take for the sample to fail. Whether you're going to compress to a known displacement, measure the force resistance, or you compress into a known force and then measuring the deflection, whatever the case may be. You're looking to destroy, essentially just test to destruction and then find out one of several things. What's the yield? What's the offset? What's the Young's modulus? What's the extension or elongation? And so on. So there are different ways of going about your tensile pool, but the objectives are usually very similar to what you would find in any other product test, as in measure the displacement when a specific force is applied, measure the force at the point where the sample fails or yields, or sometimes you can find this in most tensile testing. You want to see how far the sample stretched before it broke, and that's the elongation or the extension of the sample. In that process, you can also find the yield point or where the sample deforms. These are the main objectives of tensile testing and what to use and why. Again, just as in compression testing, primarily compression plates are used. Wedge grips. Why wedge grips? Wedge grips, you'll find those in different sizes and capacities depending on the size of the sample. Again, sizes can be dictated by your own internal standard or by an ISO standard that requires, or ASTM standard that says, hey, all samples need to be cut into 6 inches long by 1 inch wide samples, grip 1 inch on the top, grip 1 inch on the bottom. That's how samples are determined. Or if you have your own internal standard, you can also determine the sizes of the samples. The reason you would choose a wedge grip is whether it's a capstan type or a spring-loaded type, or a lever operated. The main mechanism in a wedge grip is the jaws tighten on the sample as it's pulled. The sample is pulled, or while the sample is under tensile load, which is ideal because the one thing you want to prevent is the sample slipping or sliding while it's under tensile load. And so wedge grips are usually really ideal. So whether it's a steel sample or aluminum or plastic or paper or textile, leather, whatever the case may be, there is a wedge grip that might just fit that application. So the added advantages when you select a wedge grip, depending on the type of sample, you have options for flat jaws, rubber faces, or serrated faces. I'll quickly explain why you would select one over the other. Flat jaws, so think of a piece of paper that you pull, let's say in a check perforation test, where you're a manufacturer of bank checks and you're looking to test to make sure that the perforated areas of that check are meeting a certain standard. If you gripped it with a serrated jaw, the sample is likely to break at the point where the jaws come into contact with the paper, which does not really concentrate the force on the serration where you want. So using flat faces, that essentially ensures that you're gripping the paper on flat jaws and then transferring the force to the point where you really need it to be, which is at the serration. You can also find certain plastics that answer the same question. Whether you're testing to a known force or a known deflection, you want to concentrate the force to a point where the force is concentrated to the middle or the center of that sample. And so you don't want it breaking at the point where the jaws come into contact with the sample. So in those cases, rubber jaws make more sense because one, you even increase that less of likelihood that the sample is going to slip because there's a little bit more traction on rubber jaws, in addition to what the actual jaws, the spring-loaded jaws, are doing in the process of tensile testing. Cases where you would use the serrated grips, as if you have, acrylic or harder samples, soft metals, and so on, the serrations or the teeth bite into the sample and prevent the sample from slipping or sliding in the jaws. So again, those are the reasons why you would select one set of jaws over another. And the added advantages, these fixtures can also come in either manual or pneumatic. Pneumatic as in samples that require a certain amount of closure force. You can kind of gauge how much clamping force is required, which you have metals that are really smooth. A higher clamping force also gives you a lesser incidence of slipping or sliding during that test application. So simple tensile test applications are the usual tensile or pull test. You'll hear the two used interchangeably. Oh, we want to do a pull test, and these samples can vary from textiles to rubber to soft metals to paper to plastics and so on. And or in certain applications, you'll see peel and adhesion strength testing or pull out or tension testing in other instances. Other sample grips that can't be used in an application are vice grips. Again, the difference between vice grips and wedge grips is sometimes you may have samples that are a little wider. So let's say you have a 4-inch wide sample. So the idea of a vice grip is a little bit more attractive rather than the wedge grip, because the wedge grips are usually intended for samples that are up to about 3 inches in width, if that. Vice grips, however, have jaws that are able to accommodate even wider samples, but other than that, they work very similar to what a wedge grip would do. However, instead of the self-tightening jaws, this relies a little bit on the operator to tighten, either using the double action or the single lever. And these can accommodate different types of test applications. So these will come in different sizes and capacities. Whether they're steel or aluminum will depend on the type of sample being tested. Again, the added advantage of having changeable jaw sets, whether it's for flat or rubber or serrated or wave, you have those options as well. And even whether the sample is flat or round. For round samples, just as you would in wedge grips and vice grips, there are these V grooves that form around round samples and allows the operator to pull round samples. So that way on, you can get through different types and different sizes of samples. Once again, these can also be manual or pneumatic, depending on how much force is required in the test procedure. And sometimes just to eliminate any repetitive strain injury, if you're testing several hundred samples a day or per shift, instead of having the operator constantly tightening, you could opt then for pneumatic grips to make it a little easier on these calibrated hands and fingers. So those are also reasons why you would opt for a pneumatic grip. And pneumatic comes in different versions, whether it's a foot switch activated or a flip switch activated. Test applications, very similar to wedge grips, can be tensile or pull testing, peel and adhesion strength testing, pull out or tension testing. There are also other common tensile testing fixtures. If you just picked up a force gauge, likely it's going to have a test hook. These are very simple test applications. It's going to be a large, medium, or small test hook that's included with a force gauge to measure simple tensile forces. There is also a flip cap accessory or flip cap hook, which is dedicated to just testing the flip cap strength or the flip strength of most containers. So in this case, as you can see here, all it does is it goes down, and on its way back up, it grips that flip aspect of the cap and pulls it open and measures the force resistance, or how much force it actually requires to flip that cap. And then there are cam grips that are also used in certain test applications. Bollard grips that are used for ropes, yarns, and so on. And then the crimp receptacle, which is dedicated to crimps and connectors. So in this instance, what you're looking at here, it can accommodate about 8 different sample sizes for the different wire gauges. All you do is just slide the wire in there, and the connector pretty much gets caught in the middle of that grip. And then that way, all of the force is concentrated on the crimp and not necessarily on the wire. So again, The common test applications that you would find using any of these fixtures would be loop strength testing, which is where you would use a test hook. I did mention flip cap strength testing, film tension testings, where you use your cam grips. Your bollard grips can be used for rope, wire, or yarn tensile testing. And then there's the cable crimp receptacle that's used for cable crimp connector testing, and also some pull-off or pull-out testing applications. There are also other application-specific custom or 3D printed fixtures. Now, I'll start with 3D printed fixtures. These days with modern technology, if there is an application that requires very minimal forces. Now, for any of these test fixtures, they're either made out of aluminum or steel. So what if you're testing the eyelids of a frog for a company that's trying to come up with solutions for surgery, or something like that requires such minimal forces that attaching any of these stainless steel or aluminum to a really low capacity load cell is not an option, because one, you're overstressing the load cell, and two, it's overkill for an application like testing the eyelids of frogs, right? So in those cases, you 3D printing a fixture, one ensures that you're printing a grip or fixture that's dedicated specifically to that application, and also providing a product that is light enough to accommodate both the load cell and the sample being tested. So there are certain custom applications that we would 3D print fixtures for. And then in other applications, like say pulling the eyes off of a teddy bear, just to see how much what the sewing strength is to protect children. Because the first thing kids do when you give them a stuffed animal is they try to put the eyes in their mouth, and then eventually they may bite it off. In order for it not to be a choking hazard, this is something that we do test. And a multi-jaw grip essentially performs that. It's like teeth just forming around that eye and trying to pull that off. You can do the same thing on a shirt or clothing buttons and so on. The floating and assisted peel test. So the floating peel jig is used for 90-degree testing, just as the assisted peel table is, to maintain 90 degrees as any sample is under peel or adhesion strength testing, to maintain that 90 degrees in the test. Again, 3D fixtures for low force testing applications, or for custom fixtures for which there is nothing off the shelf that meets it. We might design something out of ABS plastic and just to 3D print it. All right, finally, torque testing. Now, torque testing, quick primer. Torque is essentially just a twisting that causes rotation. Every time we talk about torque in my many years of doing this, everybody's thinking about vehicles, right? Oh, your Mustang has this much torque. I'd like us to move away from the vehicle torque more to practical torque, pretty much to you grabbing your favorite beverage out of the refrigerator and just having a hard time just getting the cap off. That's the kind of torque we're talking about. Or the amount of torque it takes for your ceiling fan to rotate and provide comfort, on a very warm summer afternoon. So those are the types of torque that we usually would be discussing in any kind of torque testing application. So in physics and mechanics, apparently, it's the rotational equivalent of linear force. So the force that causes an object to also rotate about an axis. And as I just gave you two examples, static or reaction torque at a slow rotational rate of speed, aka taking the cap open on a bottle, or rotary or dynamic torque, which is a constant spin or continuous rotational rate of speed, like a fan or a motor, and so on. So these are the types of torque that's usually measured in a typical torque testing application. So there is an application torque, which is that closure torque. Now, before your favorite beverage gets to you, it comes down the line and there's this hydraulic torquing equipment that's applying this specific application torque to cap these products at 10-inch pounds, 15-inch pounds, whatever the case may be. So once the product gets to the market, we expect consumers to be able to just get into their favorite beverage without having to have a wrestling match. However, if that capper is applying too much torque, it has a direct relation to the struggles of the consumer, right? So torque testing then ensures that the right amount of closure or application torque is being applied, and that translates to the ease of opening the product. Now, not simply easily opening the product, but also just enough torque to keep the product fresh while making it easy for consumers to open product A in order not to get them going over to product B. So application torque, that's the closure torque, and then the release torque is either the opening or the release. And then rotational torque is more of a dynamic torque, just measuring the torque resistance when a certain piece of equipment or motor, for example, it's spinning at a certain rate of speed, 1,000 revolutions per minute, 5,000 revolutions per minute, whatever the designation may be. So these are the types of torque and what to use and why. So we'll look at a few of our torque fixtures. In a typical torque application, which is in that image you're looking at there, one of the things you're looking at is a saddle plate. That means that when the operator fixtures any sample, we expect it to sit flat. So if you have 10 different operators on different shifts running, everyone's going to do the exact same thing at the exact same time. Sample has to sit flat. Next thing is you have a V block or precision fixing plate that is provides these unique silicone fixing pegs that form around both the base and the cap to prevent the cap from spinning. The advantage of using these universal pegs is you can go through different sizes of containers using the same fixtures by moving those pegs to different areas on either the upper or the lower fixing plate. So let's say you have a simple 2 milliliter bottle versus a 15-liter bottle. You can accommodate all of the above samples all with using the same fixtures and so on. So test applications will involve samples that are round or square or hex or non-symmetric, because those pegs can be moved around to accommodate either the cap or the base of the testing sample. For most closure or release torque applications, you'll find mandrels that are, so one of the disadvantages of using the universal fixturing is each operator has their own concept of how tight is, so to speak. So if you have an operator who's a little heavy-handed and they're over tightening on the cap, that might cause a little bit more torque resistance than is necessary to uncap that container. So that might skew the results a little bit. Whereas if you have a typical serrated cap, as you would find on any of the soda bottles you'd find out there, it makes sense to use a mandrel that is molded to those serrations. And that way, that essentially eliminates any variability in how the samples are fixtured, because all the operator is doing is essentially dropping the mandrel onto the cap. No need for tightening whatsoever. I've also seen instances where even the base, if it's uniquely shaped, is molded, so there's no need for tightening on the base. Now you can kind of get away with over tightening on the base because all we're trying to do here is concentrate all of the torque on the cap anyway. So if you have a mandrel or a chuck that can be molded to the shape or the serrations of the cap, that's golden. There are also instances where the cap might not be serrated and it might be glass or plastic or aluminum and it's smooth. So those are instances where we have the serrated split mandrel that has the serrated teeth to kind of create these more of a tightening fixture on the caps as you perform your torque testing application. So you'll find these on either circular, you find circular type chucks or mandrels, split mandrels, or the peg driven. Peg driven essentially just allows you to mount it to the sensor assembly that comes with some of our torque testing equipment. Testing applications are corks on spirits in bottles, roll-on pilfer-proof caps, rub caps, plastic caps on PET bottles, and so on. And then they're also in the mechanics of things where you're not looking at containers necessarily, but you're actually looking at actual mechanics, things like torque screwdrivers or bolts and nuts and so on. There are dedicated chucks that can be used anywhere from a 3/8-inch Jacobs chuck up to a lathe style chuck that accommodates slightly larger samples. So you'll find these test applications in catheters, automotive knobs, large mason jars, torque screwdrivers, as I mentioned previously, and lately even lure locks in the medical device industry because of the unique shapes some of these chucks and mandrels usually come in handy in those test applications. So these are essentially the types of samples, types of fixturing that you would find in typical compression, tension, and torque testing applications. Final topic we'll look at here is the troubleshooting of common issues that affect the repeatability and inconsistencies in testing applications. And these are pretty much universal across the board, whether the testing is for tensile or compression or torque. First key factor is the definition of the testing objective. Anytime you pull out the tester, put a sample on it, what is the goal? What are we looking for? Because you'll be amazed, there are instances where you sell a typical sophisticated tester and people still operate it manually. And then if the numbers are all over the place, end users might wonder what's happening because there's no clear definition of what the testing procedure is. Now that can be one state out definition. You define the testing objective. What are we looking for? Are we looking for how tight these caps are? Are we looking for the bounce rate of a tennis ball? Are we looking at the tensile strength of zip ties? Are we looking at the collapsibility of these corrugated cardboards? Are we looking at the tensile strength of steel rods? Whatever the case may be, an objective needs to be defined. What is the goal of the test? And then having defined that, the next thing is the how. How do you get there? Ideally, if there's an ASTM or ISO standard that's already preset, say, hey, for all these plastics, use ASTM 638, D638. That's a typical tensile test that defines the speed of the test, the sample size, and then the calculations, what kind of data you're looking for. Easy peasy. You can go by that standard and make sure you're testing according to that standard. However, if it's an in-house standard, then you also need to kind of set some rules for your operators on exactly what needs to be done as far as the testing application sample. How fast are we going to run the test? What does a typical sample look like? And so on. And then the next question is using the appropriate testing equipment. When we've defined the objective and we know what the testing procedure is. So for example, if we require a constant rate of speed for the test, then obviously manually driven or hand operated testers are completely out of the question because we need to run at a constant rate of speed, which means we're better off looking at a motorized tester. So the selection of the appropriate testing equipment dependent on the objective and the test procedure, that's critical to eliminating any inconsistencies in the test. Once the proper equipment is set up, is defined, next thing is the ideal grips. And hopefully a short discussion here on grips and fixtures for compression testing and torque has been helpful in determining the types of fixtures. There are always going to be instances where unique fixtures are required because the sample or the under test is so unique. That's also okay. We're always happy to help partner with you to come up with the best possible custom fixturing that not only ensures you're testing consistently, but also that operators have an easy time just fixturing the samples to eliminate any inconsistencies in the process itself. And that brings me to my next step, developing standard operating procedures for operators and staff. So it's not just about having the right equipment, having the right fixturing. The next big question is everyone doing the exact same thing every time? No one's taking shortcuts. Sometimes it's a little difficult to program humans, as you know, and so making it almost impossible for users to deviate from any standard operating procedure is important. And one of those, for example, in torque testing is that chuck. Each operator has no choice but to drop that chuck on the cap. They can't go about it. They can go halfway, they can under tighten, they can over tighten. They're all going to do it the exact same way. Same way with that saddle plate. We want the samples to sit flat on those saddle plates. Same way with wedge grips. We need to feed the sample into the wedge grip, release the lever, and it will just self-tighten on the sample. So again, selection of grips, critical, not only for the application, but also to make it easier for operators to fixture the samples, which is critical to consistent testing. And then finally, If every single box on this slide has been checked off, the next thing is, if there's still inconsistent testing results, then it's time to look at the product itself. What's happening with the product? We've defined the testing objective. We know exactly what the testing procedure is. We have the correct tester, we have the correct fixtures. All the operators are doing the exact same thing each time, but these numbers are still all over the place. What could be the problem? And I'll throw a very quick example in here. We had to test mason jars that are used to bottle legal moonshine. Yes, there is such a thing. And the release torque was just impossible. I mean, they were very high value release torque values, and they were all over the place. So we were trying to figure out what the problem could be. So come to find out, just in the process of bottling and capping, anytime there was any splashing or spillage and some of the product went into the threads of the mason jars, it was creating sugar crystallization, which was further applying certain tightness to the caps and just making it impossible to open. So it wasn't just a regular cap on a simple glass jar, but there were additional factors. So those are some of the instances where after you've checked off every single box, you go back and look at the product. And in this case, we were able to identify the crystallization of the sugar that was making it even tighter and impossible to get those caps open. So these are all the different factors that affect consistent and repeatable testing. So once you've addressed all of these, we are pretty confident you should be able to establish a repeatable testing environment. And with that, we will bring our webinar today to a close. As I said, these are usually presented into a little bit more detail over 3 different webinars separately: compression, tensile, and torque, with sometimes real life experiences and real life scenarios. But for the purposes of our fundamentals, we just wanted to just quickly touch on this and provide you all with as much information as possible. And with that, I will turn you all over to my colleague, Sharon.
Thank you so much, Moses. So I'll give everybody a few minutes to just gather their thoughts. If you have a question, now would be the time to enter it into the question box if you have not already done so. So we'll just wait and see if there are any questions that are coming up. Moses, I have one question. It is, what if none of these fixtures work for my application?
Excellent question. So we will work with you to come up with the appropriate fixtures. So part of our process here at McMesson is we have a virtual demo that allows our prospective end users like you would send us some of your fixtures, and we'll do our best to match them up with the right type of equipment and the appropriate fixtures. Whether it's something that's off the shelf or, as you just mentioned, none of these, none of the above, we'll still get a way to design custom fixturing that meets the same objectives of preventing the sample from slipping and also allowing operators to consistently test the sample to give you repeatable testing results. So yeah, we're ready to work with you to develop custom fixturing at any time. It doesn't necessarily have to be any of the ones we discussed today. Back to you, Sharon.
Awesome. I have another question. Sorry, I just want to enlarge it so that I can actually read it. Do your measurement machines have the facility to capture the electrical switching point of a switch on the force displacement graph?
Yes. Yes, so our I-series testers actually have an event recorder which measures the switch or close. We've had applications in the past on Weber grills that measures just when the grill turns on, or on a touchscreen, we have a touchscreen actuation that indicates when the probe makes contact with the touchscreen on the actual actuation of when the switch opens or closes. So yes, there is a way to measure the electrical signals on the on or off, or switch open or switch close. So there is an event detection that's inbuilt in our I-series testers.
Awesome. Thanks, Moses. Another question. How do you, oh, sorry, just as I was about to read it, how do you center up the fixtures on the multi-bolt location mountings? I'm not sure if I read that correctly. Does it make sense,
Yes,
Moses?
yes, it does. So in if you're referencing any of our dual column or single column testers, the base plate does have multi-bolt mountings. However, there are sliders on the side. So there is this slot on that base plate that allows you to loosen the bolts, to move it forwards and backwards, to line the samples up with whichever upper fixture to make sure that the fixtures are symmetrical when you run your test. So yeah, that's the best way. So again, if you're testing using, say, a large wedge grip, for example, the center bolt hole is a 5/16 threaded hole. So ideally what we would recommend is just remove the two outer holes, which is the 1032 and the M6, and just concentrate on that 5/16 hole. But if you loosen the 4 bolts that hold that base plate, you can move it back and forth to center it right below the sample, so you can properly test it without having it being crooked.
Thanks, Moses. Next question. Do you have a recommended fixture for holding an implantable pulse generator or IPG for connector insertion and retention force testing?
It's difficult to just say that as an abstract. Now, I'm familiar with parts of an insertion and removal test, but it's all going to come down to the size of the sample or the thickness of the sample, you know, because all we're doing is making sure you have a way to grip that base fixture and then a way to grip the top fixture. So the whether is it round, is it square, is it unusually shaped? So if we have a little bit more information on this particular sample, I'm sure we'll be able to either recommend something off the shelf or come up with something custom.
Awesome. Next question. How can one be sure if the sample is not deformed in the wedge grip to see if it is deformed or not? Does that make sense?
Yeah, I'll try to. So is it deformed in the wedge grip or not? By deformed, I'm going to go out on a limb here and assume, let's say, just rubber inside serrated jaws. Are the jaws actually eaten into the sample, and so it's already deformed before you start testing? And that was one of the reasons for the point I had made is, first we look at this type of sample being tested and then recommend the types of jaws that should go into that wedge grip. So if it's a plastic or rubber or soft material, then we want to stay away from anything that's serrated to prevent any deformation of the sample in the wedge grip. So in that case, either rubber-faced or flat-faced jaws will eliminate that issue completely. The only other deformation I can see is if the sample is not properly scored, or it's not cut evenly, or it's not properly fixtured, then that's more of a sample preparation and sometimes even an operator error. So those are all some of the issues that go into determining whether or not the sample is properly fixtured. But as far as the type of material, we should be able to determine the types of inserts to use for the wedge grips. Back to you, Sharon.
Thank you. Next question. What can be some of the types of quick release jaws / grips that can be used if that is our requirement?
So thanks for the question. Most of our fixtures and jaws or grips are either threaded. And so if you're looking for quick release options, we actually have quick release adapters. So that way, if you have multiple testing applications, so for example, you have a sample that's both a pull-off and a compressive, we have quick release adapters that you can attach to both your compression plates and say your wedge grips or your vice grips. So once you're going from one application to the other, you just pull a pin, remove one, put the one fixture on, pin it, and then move from one application to another. So either we might have some that come off the shelf with the quick release adapters installed, or we have quick release adapters as an additional peripheral that you can add to any of our screw ones that actually are grips and fixtures that have screws. So you can attach those and essentially convert them to quick release fixtures and grips.
Thanks, Moses.
No problem.
How can I define the correct torque value to ensure repeatability of results?
Oh, this is a tricky one. Let me just put this out there, and I've been fighting this battle for 17 years. There is no real relation between application torque and release torque. There is only to the extent the higher the application torque, the higher the release torque is going to be, but there's no clear-cut table out there. There's some that says if the application torque is 20 inch-pounds, then the release torque has to be 10 inch-pounds or 12 inch-pounds, or just 50%. No, it's all going to differ depending on the type of sample you're testing. Is it a glass jar with plastic caps? Is it a plastic container with aluminum cups? Is there too much friction in the threads? All of that is kind of affects the type of torque values you're getting. It's difficult to make a determination. The only way to establish a testing standard is to actually test. So in this instance, what I would recommend is grab 12, 15 samples, determine a specific testing application. If the containers or the samples are already capped, determine, all right, these were capped. We're not, whether you're sure of what the application torque was, we'll just say we're going to run all these samples at a known speed of, say, 10 revolutions per minute to a known angle of 360 degrees, and then measure whatever that release torque value is. If they're consistent or within a certain acceptable range, then that's essentially the guide you're going to use. It's a bit difficult for me to say, hey, you know, on this brand A, you should look at 15 inch-pounds without knowing the processes that went into the actual application torque, or what other circumstances there might be vis-a-vis the crystallization of sugar on a mason jar for a moonshine producer. So it's all about establishing a testing standard that's consistent in order to generate consistent testing results. Now, if those numbers are consistent or within a certain acceptable range, great. If they're not, it's time to look at what the capper is actually doing on the line. If the capping manufacturer's recommendations or specifications are saying the system is applying 20 inch-pounds of torque, there is a way to have any one of our systems duplicate that by applying a known application torque and then running your release torque test. And 99% of the time, you'll see release torque values that are more consistent, and that immediately kind of shifts the attention to whatever the capper is doing on the line. Sorry, that was a long-winded answer, but it's also a really difficult question to answer. Back to you, Sharon.
Thanks, Moses. So we've got a few more questions. I'm going to try and get through all of them.
Sure.
Do you have a fixture for peel test of small samples at 45 degrees according to ASTM F2824?
Yes. Yes. So it's yes. For now, I'll just say yes, we do. The next question, obviously, is what's I heard small, but small should always translate to the sample width and the sample thickness, and that should essentially help us determine which fixture attaches to the gauge. As far as that base fixture, we can rotate that to 45 degrees to maintain a 45-degree angle as the sample is actually peeling. So yes, the answer is yes.
Thanks. Next one. How does the 90-degree peel strength modules work? Since we test the welding quality of cell connectors on 18650 standard cells, and the welding spots are not always on the same spot.
So the test application on a 90-degree test is usually either, as I mentioned, the fixtures that I showed you are essentially just a peel table, a sliding peel table, or a floating peel jig. There are also the T-peel, where if you took the top, think of, say, a laminate on a table. If you grab one part of the table, grab one part of the laminate and just peeled it apart, then you would be able to measure a certain weld strength. This is one of those questions that requires a little bit more detail. We need to see what those samples look like in order to kind of assist in detail how you can approach testing those. So if you could reach out to me directly, if you want to send samples here, we'll do a virtual demo. It's at no cost to you. We're happy to do that just to kind of arrive at the most ideal grips and fixtures for your application, so we can help with that.
Thanks, Moses. And the next question, does McMesson have data on typical compression force pressure curve the wedge grip will exert on sample as tension load is applied? Context is destructive pull testing of terminals on wires, for example, bootlace ferrules.
Yes and no, only because crimpers are as varied as the industries you'd find them in, or the different organizations you find them in. However, there is a guide, either a mil spec or a UL spec, that specifies whether it's ferrule type or typical crimp connector type, on the size of the cable and what the expected minimum force values should be. So I do have that data. If you have the sizes of the samples you're testing, we can run them through that data to say, hey, on this 14 gauge ferrule type connector, we should be looking at a minimum threshold of 100 pounds. If you apply at a known rate of speed and just apply the 100, obviously, if because a connector comes off before it hits that minimum of 100, then it was a bad crimp to begin with. But again, results are going to vary from industry to industry because of the types of crimpers that are used. I wish there was just the one crimper that's used by everyone that would help us determine that standard. But there is a guide that kind of gives us an idea of how much force the minimum thresholds on each type size of cable should be. So we could use that guide. But as far as actual data on what we've done in the past, those are, as I'm not sure it's going to be of any use to you because they differ from company to company to company.
Awesome, Moses. I think we're at the last question, and that is, can we do untorque testing at the same time, which is measuring clockwise and anti-clockwise rotation torque?
Absolutely. That's my favorite test, actually. I did a few minutes ago, I mentioned duplicating what the capper is doing on the line. So if the manufacturer of that capping system says, oh, we're applying between 18 and 20 inch-pounds to cap all of these containers on the line, for example, you can duplicate that in one of our automated torque systems and say, all right, let's cap each of these bottles to between 18 and 20 inch-pounds of torque. Pause for 10 seconds, 15 seconds, 15 minutes, whatever the case may be, and then release the torque, all within the same torque test application, and then capture data for both the application and the release torque within the same test. So the answer is absolutely. Do that all the time. Again, if you'd like to see it, reach out, send some samples over. We'll give you a one-on-one demo so we can answer all your questions on a one-on-one.
So much, Moses. That was a mouthful. So really appreciate
no problem.
You sharing that. Thank you everybody for attending. And as Moses said, you can reach out to us at info@mcmesson.com, or if you want to speak to Moses directly, his email address is moses.derosha@pptgroup.com. But if that's a lot for people to scribble down now, the invite that you received for the webinar, the return on that is my address. So it's Sharon. And there we go. Moses is actually busy putting his email address in there. So if you guys want to reach out to him directly, please do that. Or you can just press return on the invite that we sent on the original webinar, and I will make sure that I channel it to in the right direction. Thank you, everybody. This was a great session, and yeah, we'd love to hear from you, and we hope to see you on one of our upcoming webinars. So keep in touch. Thank you very much and have a great day.
Thanks, everybody. Thanks, Sharon.
Thanks, Moses.